Hello everyone, and it's a pleasure to have here today YueYue Shen from the National Astronomical Observatories of the Chinese Academy of Sciences. She is a PhD student, and her supervisor is Professor Xiaoyu. She is here for 1 year in an exchange program, and after a competition, she had to pass to get permission and financing for her stay here. She is down on the 3rd floor, and if you want to meet her, and if you don't know her yet, and she will be here for quite a long time, so you will have time to interact with her. She is working on stellar clusters, open clusters nowadays, and she's done work on the initial expansion of young stellar clusters, and she's now moving to something related to the metallicity distribution for her PhD.
Thank you, and good afternoon, everyone. Today I'll introduce the project I've been doing in the past 2 years, which is the stellar mass function in young open clusters, and also the things I will be going to do in the following year, the metallicity of them. So first comes to the mass function. The distribution of stellar burst masses is described by the initial mass function, IMF. And as one of the most fundamental assumptions in astronomy, the IMF is extremely important as it because it affects all physical models at all scales, from gas and dust to stars, clusters, and galaxies. It has long been an important yet controversial topic ever since it was first proposed by Salpeter in 1955. Debates have continued from its origin to the mathematical form, and whether it is universal or variable. And some of the historical IMF measurements include those by Salpeter, Miller et Scalo, Krupa, Chabrier, and Dimaci, with the terms of single power law, broken power law, and tapered power law, and log normal distribution, respectively. There are many ways to measure the IMF. The direct method is to start with star counting, and then convert it to the stellar luminosity function with the observed or theoretical mass luminosity ratio. The mass function can then be derived. And there are also various indirect methods for unresolved populations. And these indirect methods usually rely more on models compared to the direct approach. So numerous studies have been have been carried out to measure the IMF in the different types of galaxies, and some have found that the integrated IMF is varies with velocity distribution and dispersion and metallicity in early type galaxies. As for the as through resolved star counts, several studies have also carried out in the Milky Way. Li and Liu found that the field IMF in the solar neighborhood varies with metallicity. Another important site for resolved star counts is in star clusters. Historically, most studies have been focused on globular clusters and with fewer on open clusters. And in galaxies and in the Milky Way field, they are both mixed population, and they are the results of multiple star formations. So as a single population, well, at least in star clusters and those globular clusters without multiple populations, star clusters are in principle ideal environments in which to study the properties of mass functions. And they should serve as better probes for measuring the IMF. However, the mass function, what we measure in star clusters is actually the present day mass function rather than the initial one. Due to the dynamical evolution, low mass stars gradually escaped, and the binaries are disrupted, and massive stars evaporated from clusters. These process together leads to a PDMF that differs from the IMF. Therefore, we choose to focus on those young open clusters with younger than 100 megayear, which are not yet undergone significant dynamical evolution, at least compared to the older globular ones. So the effects of dynamics are expected to be relatively small. Another challenges in measuring the mass function in clusters is the membership identification. So first, cluster identification is a non-trivial problem. And usually we rely on 5D parameters to select the member stars from the observation sample, which can introduce contamination from the field stars. And besides, different clustering algorithms can produce different numbers of member stars for the same cluster. Since the mass function relies on the star counts, such differences should be carefully evaluated. So I will present my work in three parts. First, it's the selection function. Second, the determination of cluster properties from color magnitude diagram. And third, the metallicity from spectroscopic surveys. So as mentioned before, the first thing we need to consider is the selection effect. For a given star with parameters Q, the selection effect is caused by three aspects, and which will lead to completeness of member stars and contamination from the fields. And they will have effects on mass function and binary properties. So based on the simulation data, the MOC field is generated from the catalog by Rybitsky 2022, and it is designed to reproduce the selection of the Gaia survey. And the cluster, MOC cluster are taken from embodied simulations using PATAR. The same selection criteria are applied to the 4 datasets to obtain the selection of the subsample. And as for the main focus, we tested 3 different algorithms and evaluated different selections introduced by each of them. This is an example of the MOC data, and the member stars are represented by red, and the field stars are gray. And the algorithms we focus is 3 widely and popular and widely used algorithms. So first, it's HDB scan, the theoretical density-based clustering algorithm, and PyUpMask is a Python implementation of UpMask, which combines multiple statistical approaches. And StarGo is an unsupervised data reduction methods based on self-organizing maps. The performance metrics in our study are defined by as completeness and contamination. This is the cluster recovery results and the overall performance for 3 different algorithms. For the cluster recovery results, StarGo recovered the largest number of MOC clusters, and HDB scan filled in low mass clusters and high density ratio clusters. For low mass clusters, they are small and harder to detect. And for high density ratio clusters, the situation is the opposite. The field stars are sparse, and they are basically swallowed by the cluster members. So makes it difficult for HDB scan to establish a clear boundary between cluster and the field populations. And for the overall performance, HDB scan achieved the highest completeness and with lowest contamination. For each observation, like open clusters, we estimated the mass-dependent selection function in terms of the completeness and contamination. With the selection function and the membership catalog, we can then determine the cluster properties from color magnitude diagram. So we built this forward model based on the color magnitude diagram to estimate the mass functions. We used the stellar evolution model parsec to create synthetic CMDs, and by combination with Bayesian analysis, we obtained the cluster properties of the observed CMDs, including age, extinction, mass function power law index alpha, and binary properties. This is the post area distribution from MCMC. So compared to other studies, our methods considers more factors because the isochrone parameters and the mass functions are all simultaneously considered. And this reduces the computational chain and avoid introducing new errors. Also, we considered more detailed unresolved binaries, and we derived the mass function statistically rather than the single stellar mass. As for the main results, you can see in the first figure, there is a clear declining trend caused by long-term dynamics after 100 million years. However, before that, there is also a peculiar dip around the 30 million age range, which appears in all three samples. And we have done some tests to try to investigate this feature, and none has provided as a definite explanation so far. So there are several possible causes, and the most promising one seems to be that this dip is caused by the early dynamical evolution of the clusters. And we are still working on this issue at the current stage. If this implementation holds after further examinations, it would imply as that we cannot rely solely on the observation data to obtain an approximate initial mass function. Additional information from simulations still necessary. And as for the rest two possible connections of largest nearby superbubble and primordial binary clusters, the main factors that prevent us from exploring further these possible two scenarios is the uncertainty of age. So to improve the age determination, metallicity plays a crucial role. You can see in this figure, the y-axis represents the metallicity and the corresponding age when the Fe over H is fixed by the from the apogee data, and the y-axis is those when Fe over H as a free parameter only with prior as a constraint. So from the left panel, the photometric, we can see that photometric metallicities can only serve as indicative values for individual clusters and should not be used for statistical analysis. And from the right panel, the age is overestimated by up to 0.2 dex when the Fe over H is a free parameter in our fitting method. So the third step is we focus to incorporating spectroscopic information, including metallicities and radial velocities for young open clusters. It helps us to break the age metallicity degeneracy, and with more spectroscopic metallicity for young open clusters and more accurate age determinations, we can also trace the present-day aerial abundance gradient and give constraints on the star formation environment. For the spectroscopic survey, we enlarge the young open cluster sample to younger than 300 megayear and within 2 kiloparsec, and by cross-match the spectroscopic surveys with Hunt and Bradford catalog, we obtain high-resolution open clusters. For high-resolution surveys, we obtain 60 open clusters from Occam, Gala, and Gaia ESO. And for the low-resolution spectroscopy surveys, we use the AFGK catalog from the Lamos data release 12 data, and we apply the same Monte Carlo sampling as in Fu and Bergalia 2022. And we also apply the RV cut and the effective temperature cut as quality control. This is the preliminary results of Metallicity. There are 254 open clusters with FE over H, and it's 100 more compared to the previous works based on data release 8. And the comparison between high resolutions estimations, the difference is minus 0.03 dex. Also, this is the radial velocity results. Totally 320 open clusters with radial velocity, and in which 243 are with high quality. The comparison between Talik 2021 and Diaz 2021 is about 5.5 kilometers per second. So finally, as you can see, we are still halfway through the journey to the IMF. And in the future, we plan to, we will continue working on spectroscopic metallicities for young open clusters, and of course, looking forward to the upcoming foremost data. And additionally, we plan to carry out embodied simulations to hopefully disentangle the variations of mass function caused by non-universal IMFs from those due to the dynamical evolution of the clusters. That's all. Thank you.
Okay, questions for the speaker?
Thank you. You were a beautiful talk. So my question is on the selection function. So it's always tricky to get a selection function, and I was wondering what are the parameters your selection function depends on?
Parameters means the physical parameters.
Yes.
I have this appendix. I think I compared the completeness and contamination results with distance, the mass of the cluster, age, extinction. These two are the number density, and these two are the number density and the mass density. And I think the main physical properties is the distance of the clusters. As you can see, with increasing distance, the completeness drops, and the contamination increase.
So there is no binary fraction yet.
No, the simulation data, there is no binary in the simulation data.
Okay, I see.
I have a clarification to ask you. You explained deep at the age of 30 mega years. Can you clarify again? I didn't get the deep was in what and what are the possible explanations? Alpha.
The dip is at the with lower alpha. The alpha means the minus alpha, and which means it's more top heavy. The alpha range is well, I've tried different mass ranges, but it's basically above 0.4 solar mass. So it's which means the mass function slope is more flat with smaller alpha. Well, in this in this age range, and with relatively more massive, not that massive, but more massive stars.
And the explanations for this you mentioned. So the possible explanations for this feature are what? You just explain again to me.
Maybe it's because of the early dynamical evolution, which is I have this appendix as well, but it's very preliminary results as well. There is a remarkable fraction of clusters younger than 300 million years, and they are currently experiencing significant expansion. And this expansion can be partly explained by the early violent relaxation process in the clusters, and so they will lose present-day mass. And I've compared well, you can see in the middle panel, but the x-axis is the alpha and the y-axis is the extent of expansion, VR over sigma r, and with clusters like with so these low alpha clusters may have already been undergone the process of violent relaxation, and they lose the present-day mass, and well, especially the smaller low mass stars, to make them like these low alpha, which means top heavy, which means the slope is more flat.
Okay. Was there a question?
Yeah, but I noted about the second of the super bubble, but I understand it's quite complicated. Maybe you can discuss it later. Can I ask you another question? When you show the radial velocity, I see something systematic. If you were to like this one, yeah. Why do you understand why there is always a systematic shift of this 5 kilometers per second with respect to the other ones?
I think it's because the third one is actually based on the Lamos Gaia. Oh no, Lamos data release 8. So they're basically the same. But the previous two, I think the offset is mainly due to the there's a systematic offset between Lamos and Gaia. So, and this offset is like 405. I couldn't remember clearly, but it's
Okay, so it's a spec.
Yeah.
Yes, and I have another question. This result comes from your simulation or from the actual observation?
the radial velocity. Oh.
Maybe all the shows now. Okay.
The selection function comes from the simulation, only that.
I mean, this data point come from your simulation or from the real observation.
You mean this one, the radial velocity?
I mean, one of this.
There comes from the observation. Observation.
And where is your simulation?
I don't have simulation of spectrum.
Or maybe the thorough earlier, maybe you can take chart.
That.
Or maybe the color magnitude diagram.
Oh, you mean color magnitude diagram? This one?
Yeah, maybe. Yes, you have simulation here?
No, it's forward modeling. The unbounded simulation only appears in the first selection function work.
And how do your simulation can represent the real relation?
Sorry, what do you mean?
Maybe I don't understand what you are showing, so maybe we can translate.
Yeah.
Any more questions? Right, okay, then thank you for speaking.